work on this. So we're going to need to fill in, we have 1 bit that's a sign bit, 8 bits that are for the exponent, so 1, 2, 3, 4, 5, 6, 7, 8, and then 23 mantissa bits, so 2, 3, and we're doing excess 127. All right, let's work through this one together. So I'm going to go through the binary number again just for review. So we want to, since this number has both a whole number and a fractional part, we need to find the binary numbers associated with those separately. So I'm going to start with the 194, and so this is the one, like since we're dealing with a whole number, we just divide it by 2 each time. So 194 divided by 2 is equal to 97, and so really it's 97.0. Since we have a 0 here, we have a 0 for that bit. Then we take the 97 divided by 2. This is equal to 48.5. We have a 0.5 here, so we're going to put a 1 for this bit. Then we take 48 divided by 2. This is 24.0. Since we have a 0 here, we get a 0 for that bit. 24 divided by 2 is 12, and so we're going to have a 0 for this bit. 12 divided by 2 is 6, so we're going to have a 0. 6 divided by 2 is 3, so we're going to have a 0. And then 3 divided by 2 is 1.5, so we're going to have a 1. And then we take the 1, so 1 divided by 2 is equal to 0.5, and so we have a 1. And we keep going until this number is equal to 0. So then we can write our binary number, and so we just take so we have 1, so we start here, so 1, 1, 0, 0, 0, 1, 0, and this is base 2. And you can verify that you get the correct number if you want by just doing some math to convert it back into a decimal. So remember, this is 0, 1, 2, 3, 4, 5, 6. Actually, something's wrong. Yeah, I missed a 0. So 0, 1, 1, this is 5, 6, 7. So then we can just say 2 to the 7 plus 2 to the 6 plus 2 to the 1, and that should work out to 194. Okay, so now we want to do the same thing with the fractional part, only with the fractional part we're going to be multiplying by 2 instead of dividing by 2. So 0.375 times 2 is equal to 0.75. So we have a 0 for that bit, and then we take the 0.75 times 2, and this is equal to 1.5. So we have a 1 for this bit, and then 0.5 times 2 is equal to 1, and so we have a 1 for this bit. And so then we can put our number together. So I'm going to take this number and combine it with the fractional part. So I have 1, 1, 4 zeros, 1 0, 0, 0, or 0, 1, 1. And this is base 2, and this is equal to 194.375. Now what we need to do, so we have our binary number, now we need to put it in scientific notation. So we're going to do that by moving the decimal to here. And so that is 1, 2, 3, 4, 5, 6, 7. So 1.1, 2, 3, 4, 1, 0, 0, 1, 1 times 2 to the 7th. Now the last thing we need to do is the exponent. So I'm going to go over here with that. And so we have excess 127. We're going to add 127 to 7. So 7 plus 127 is equal to 134. And so now we have 134. We could go through the same method of dividing by 2 to get the binary number for 134. I'm just going to tell you what it is. So it's 1, 2, 3, 4, 1, 1, 0. Okay, so now we have everything that we need to fill in our floating point notation. Yeah, 0. And then we fill in our exponent bit, which is this. So 1, 1, 2, 3, 4, 1, 1, 0. And then we fill in our mantissa, which we're assuming that the first digit is 1, so we're only going to put this part of our mantissa in. So this is going to be 1, 0, 0, 0, 0, 1, 0, 0, 1, 1. And then we're just going to fill in the rest of the bits with zeros. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. The 194.375 represented in floating point notation with 32 bits. So there's also a double or 64-bit floating point notation. And so the difference between that, first of all, the sign bit is still 1 bit for both. The exponent for the 64-bit is 11-bit, and the excess is then 1023 instead of 127. The implied base is 2. That means we're in binary. And then this has, so the mantissa is 52 bits for the 64-bit, and whereas the one we just did was 23 bits. And the decimal digits that these can reasonably represent are, for the 32-bit, approximately 7, and for the 64-bit, approximately 15. And then the value range for the 32-bit would be 10 to the negative 45th to 10 to the 38. So this is the approximate value range that we can represent with these notations. And the 64-bit is approximately 10 to the negative 300 to 10 to the 300.